Good morning, students. Let us start with next part of the chapter Chemical Kinetics. We had done the integrated rate equations. Today we will talk about half-life of a period. Half-life of a reaction is the time in which the concentration of a reactant is reduced to 1/2 of its initial concentration. It is represented as T half. For a zero order reaction, rate constant is given by K equals to R naught minus R upon T. Now, at T equals to T half, R will be equal to half of R naught. Let us put these values in this expression. So, K will be R naught minus half of R naught upon T half. So, what will be T half? It will be equal to R naught upon 2K. Means T half for a zero order reaction is directly proportional to the initial concentration of the reactant and inversely proportional to the rate constant. Now let us calculate T half for a first order reaction. Here K is equal to 2.303 upon T log of R naught upon R. Again, at T equals to T half, R will be equal to half of R naught. Putting the values, you will get T half equals to 2.303 upon K into log 2. So it will be 0.693 upon K. From the expression, you can see that for a first order reaction, the half-life period is constant, means it is independent of the initial concentration of reacting species. So we may conclude for a zero order reaction, half-life is directly proportional to R naught, whereas for first order reaction, half-life period is independent of the initial concentration of reactant. Now here is a summary of integrated rate laws for zero and first order reaction, because in our syllabus we are to deal with these two type of reactions only. So differential rate equation will be minus d by dt. For first order it will be minus d by dt is equal to k into A. Integrated rate law, A is equal to A naught minus kt. For first order, it is A is equal to A naught into e raised to power minus kt. So you will get the straight line by plotting graph between A and t. Here the graph is between natural log of A and t. Slope for both will be equal to minus k and units of rate constant for 0 moles per liter per second, and for first order reaction it is second inverse. Now we also have pseudo first order reaction. Pseudo means false. This reaction can be defined as a second order or bimolecular reaction but is behaving like a first order reaction. This type of reaction occurs when one reacting material is present in great excess or is maintained at a constant concentration, so that any change in its concentration is taken to be negligible. For example, hydrolysis of esters. You can see initially you have taken 0.01 mole of ester and 10 moles of water. But after time t, ester is consumed fully, but water 9.9 moles are left behind. So we can say concentration of water does not get altered much. So such reactions are called pseudo first order reactions. If you write the rate equation, it will be rate is equal to K prime into ester into water. Now, if consider concentration of water is taken to be constant, then the equation becomes rate is equal to K into ester, where what is K? K is K star into water. So now this expression, this becomes same as that of first order reaction. So such reactions are called pseudo first order reaction. Here is a specific example. Now, temperature dependence of the rate of reaction. The maximum part from this topic has been deleted, but I am just trying to give you elementary idea of this topic. Rates of most of the reactions are very sensitive to temperature. Most of the reactions increase rapidly with increase in temperature. It has been found for a chemical reaction that rise in temperature by 10 degree, rate constant becomes nearly doubled. Let us see this reaction H2 plus I2 to form 2 moles of HI. Here you can see the bond between HH and II needs to be broken and the bond between HI needs to be formed. So in between the reaction, such type of intermediate is formed where no bond is complete. The bond between HH and II are in the process of breaking and between H and I are in the process of making. Energy required to form this intermediate is called activated complex. So energy required to form this intermediate is called activation energy. If we plot a graph between the potential energy and the progress of reaction, here this is the energy of reactants, then reactants do not change into products directly, they change into products. You will get the graph this like this. They will change into products by first forming the activated complex. So, for forming the activated complex, you require to supply this much amount of energy known as activation energy. So why the rate of reaction increases with temperature? This was because the molecules get this activation energy. It becomes easy to form a activated complex or an intermediate. And once this intermediate is formed, then automatically the product will be formed. Difference between the energy of reactants and products will give you delta H, that is enthalpy of the reaction. If we check a particular reaction, we will find that all the molecules of the reacting species do not have the same kinetic energy. If we plot a graph taking the fraction of molecules on y-axis, kinetic energy on x-axis, graph comes to be of this type. Graph comes to be of this type. This is the peak of the curve. It corresponds to most probable kinetic energy, means kinetic energy possessed by maximum fraction of the molecules. Now when the temperature is raised, the maxima of this curve moves to the higher. Now this was the maxima, but when the temperature is raised by 10 degree, the shape of the graph changes. Now maxima now shifts here, means kinetic energy has increased, but fraction of molecules possessing this energy has decreased. Earlier it was at this point, but now it is at this point. The area, shaded area, here shaded area you can see, the shaded area becomes double. This shaded area represents the fraction of molecules which can react at a temperature T. Now since the shaded area is doubled, it means the fraction double number of molecules will now react at temperature T plus 10. Now a little bit about effect of catalyst. What is catalyst? It is a substance which increases the rate of reaction without itself undergoing any permanent change. Now what a catalyst does? Catalyst lowers this energy barrier. Catalyst provides an alternate pathway with lower energy barrier. It reduces the activation energy between the reactants and the products. That's why the molecules are able to cross this barrier easily and more number of products will be formed. Initially, this was the energy of activation, but now this is the value of energy of activation. Catalyst, however, does not alter delta G of a reaction. So this is all for this chapter. Thank you.